Charged, a capacitor can be thought of as a temporary battery because it can retain the stored charge for a long period of time. However, once provided with a current path, it can release its stored energy. Let's see how the capacitor does this within the context of the DC resistive circuit.
When the switch closes, a current path is provided and the capacitor begins to discharge. During discharge, the surplus free electrons on negatively charged plate R flow back towards positively charged plate L. Again, the electron flow is from lead to lead through the external circuit and not through the dielectric. This process is called discharging, and electron flow is known as the discharge current. When all the surplus electrons have moved, both plates become electrically neutral and the capacitor is fully discharged. The voltage across its terminals is 0.
A high voltage or any high-value capacitor can produce dangerous electrical shocks and burns if mishandled. As a student or trainee, you should never handle charged capacitors without the immediate supervision of your instructor. Let's consider the proper methods for safely handling charged capacitors.
Imagine that you find an unidentified capacitor. The best thing to do in order to be safe is to check to see if it's charged with your voltmeter. This procedure assumes that your voltmeter is capable of reading the highest voltage that could exist across the cap. To discharge a cap, use insulated alligator clip leads to connect a high-value resistor across the cap. This will safely discharge it. A cap that is discharged should read 0 volts across it.
Up to this point, a graphic representation of a capacitor has been used. However, this is the actual schematic symbol for a capacitor, which you will find on circuit diagrams. Now that we've examined the charge and discharge processes of a capacitor within a DC circuit, let's take a look at how a capacitor will respond to the changing values of voltage and current in an AC circuit.
Again, a single capacitor will be used in the circuit for demonstration purposes. An AC source voltage with a peak value of approximately 170 volts will also be used. For this analysis, a single AC cycle will be divided into 4 quarters. During the first quarter cycle, from 0 to 90 degrees, the magnitude of the source voltage is increasing. The capacitor charges to keep the capacitor voltage equal to the source voltage. Charging current flows until the capacitor reaches the peak voltage of 170 volts. At this point, entering the second quarter cycle between 90 and 180 degrees, the magnitude of the AC source begins to drop off. Since the capacitor and source are in parallel, the voltage across both must be the same. This means that the capacitor must discharge to reduce its voltage during the second quarter cycle. At 180 degrees, the voltage will be 0 and the capacitor will have fully discharged. At this instant, the polarity of the AC source reverses. And during the third quarter cycle, from 180 to 270 degrees, the voltage increases toward its negative peak of minus 170 volts. As the source voltage increases negatively, the capacitor must now charge with the opposite polarity to follow the source. Charging current will flow until the capacitor reaches the peak voltage of negative 170 volts. During the fourth quarter cycle, the AC voltage drops off, moving back toward 0. And so, during the last quarter cycle, the capacitor discharges to reduce its voltage and follow the source voltage. The discharge current will flow until the source and capacitor voltages are 0 at 360 degrees.
Now that you've seen how a capacitor stores and releases energy in an AC circuit, let's look at some important terms associated with capacitors.
The indicator of a capacitor's ability to store a charge is called capacitance, designated with a capital C. The unit of measurement for capacitance is the farad, labeled with a capital F. The farad is much too large a unit of capacitance for practical electrical circuits. Because of this, the microfarad is used, often abbreviated mu capital F. A microfarad is equal to 1/1,000,000th of a farad. Another common unit of measurement for capacitance is the picofarad, abbreviated lowercase p, capital F. This unit, in effect, is a microfarad, or 1/1,000,000th of a millionth of a farad.
Stop the program and complete activity number 2. When finished, continue watching the program.